All right, welcome to chapter 21. This is probably my favorite chapter of the entire book. The walkthrough examples are a lot of fun, and this is a really advanced one, which has a lot of interesting use cases. But the most exciting part about this models out GitHub, which is very familiar to a lot of users. I'm hoping, so it's kind of fun to think about how you would actually design that. So in this one, we're going to model the GitHub metadata backend. Again, we're going to use the same process that we've used in every example. Number one, understand that application. Know what you're trying to build. Know those different pieces and how they fit together. Once you've done that, then you go out, you build your ERD so you know what the different entities, what the different objects are in your application and how they relate to each other. Third, you go out, you define your access patterns and you make a list and you say, hey, what am I trying to do here? What am I creating? What am I reading? What am I listing? What am I updating? All that stuff. Finally, once you have all that, then you get into the part of designing your table. You design your primary keys, your secondary indexes, DynamoDB streams, whatever it takes to handle your access patterns. So let's get started with that first step, which is understanding your application. As I said, we're modeling out GitHub here. I hope that's familiar to most of you, but in case you aren't, we're going to walk through this, talk about the entities, talk about what we will be modeling and what we won't be modeling in GitHub. So right here is an example repository in GitHub. We also call it a repo. This is where code is stored for a particular project. Up at the very top there, you can see that it says AWS. That is the owner of this repository, and that owner can be an organization, as it is in this case, or it can be a user. Right next to that, you see AWS-SDK-JS. That is the repository name. So this is the SDK for JavaScript for AWS. The combination of those two, the repository owner and the repository name, need to be unique across all of GitHub, which also means a repository name needs to be unique within a particular organization or user, particular account there. In addition to the repository name there, we also up at the top have this star. A user may star a repository to indicate, they like it. So it's kind of like a Facebook like, I would say. You can click on that. You can see there are 5.8 thousand likes on this particular repository. If you click on that, it'll list everyone that has starred this particular repository. In addition, you can fork this repository, which means it basically means make a copy of this repository and also point it back to its original fork. This is a useful concept in GitHub as you can stay up to date with changes from that origin repository. In addition to stars and forks, there are also issues. Users can open issues on GitHub repositories, and it's sort of like a ticket tracking thing where you can file a bug report, you can file a feature request, you can just file some sort of reminder there. In addition to issues, there are also pull requests, which are outlined there. A pull request is a request to change the code in some way in that repository. So it includes some code, also a description and a title that's saying, hey, this is what's happening in that change. And if that is merged in, then it will become part of the code of that repository. One thing I want to note down there is there are all the contents of that repository, such as the Git contents, the different files and the history. We're not doing any of that here because that gets pretty complex. That's very much a search problem and also a Git problem itself, and I didn't want to get into that. This is more about the metadata of GitHub, so repositories, issues, pull requests, users, organizations, things like that. Speaking of organizations, let's take a look at how that works. So over here, when I go to GitHub, this is my account and it has my repositories, and it also has different teams that I belong to. So I've outlined those in red, those different teams, which means I have some sort of permissions within those teams. Let's go back and talk about issues, which we saw on that initial repo page. Issues and pull requests are very similar. So I'm going to walk through issues here, and then I'm going to talk about how most of that also applies to pull requests. So first of all, when you're looking at issues, there's going to be like a get issues page that's going to show a big batch of issues for you. One thing to note here is you can filter by open or closed. So by default, an issue is open when you open it, but if someone finishes a ticket or determines it's not relevant or anything, they might close it. And so you have this filtering status of open or closed. A second thing to note here is that issues are ordered in terms of the most recent issue number first. So each issue is going to be assigned a number as you create it, and then you'll get the most recent issue number first. If we go in and look at an issue, there's the issue number there. I've pointed out 1603. One thing that's interesting to note is that numbers are shared across issues and pull requests. So when you have a new repository, you create your first issue, that's going to be issue number 1. You create your second issue, that's going to be issue number 2. Then you open a pull request, that's going to be pull request number 3 because you already have number 1, issue number 2, pull request number 3. Then if you create another issue, it's going to be issue number 4. So they increment together on each other, which is kind of interesting. Another thing to note here within an issue is that people can comment on an issue, so you can attach comments to an issue. Same thing with a pull request. And then finally, you can also have reactions on an issue. And you can actually have reactions on an issue, on a pull request, or on a comment. And there are 8 different kinds of reactions, including thumbs up, thumbs down, smiley face, heart, rocket ship, all kinds of stuff. So let's just recap what we're creating here. We're creating the GitHub metadata API. And remember, this is nothing about the Git repo contents itself. It's more about issues, pull requests, users, organizations, things like that. So we have repos, issues, pull requests, those core entities. We also have stars and forks that show people interacting with those GitHub repos. We also have comments and reactions, another way to interact with issues, pull requests, other comments. And then finally, we have that user management layer of users, organizations, and payment plans. All right, so now that we understand the application we're building here, let's build out our ERD, our entity relationship diagram. And this is what I came up with, pretty complex. We've got 8 different entities and a bunch of relationships between them. Let's just breeze through this real quick. So on the left-hand side there at the top left, you have users in a box. Users can belong to multiple organizations, and also an organization is made up of many users, so there's a many-to-many relationship between users and organizations. If you go all the way to the left, there's that payment plan box, and both a user and an organization can have a payment plan. In the middle there, you have that repo entity, and that's really the core entity in our application because you see a lot of different things coming out of it. If you look a little bit to the left there, you see a relationship where there's a fork relationship with repo, where repos actually has a one-to-many relationship with itself because a repo can be forked into another repo by multiple users. Additionally, a repo is going to have multiple issues and multiple pull requests, so there's a one-to-many relationship between repos and issues and repos and pull requests. Both pull requests and issues can have comments. So there's a one-to-many relationship going from issues to comments and from pull requests to comments. And then finally, there's a one-to-many relationship between issues and reactions, comments and reactions, and pull requests and reactions. Let's review that quickly just to summarize. We've got 9 entities: repos, issues, pull requests, reactions, comments, forks, users, organizations, and payment plans. We also have 15 relationships. 2 of those are many-to-many, 11 of those are one-to-many, and then there's 2 one-to-one relationships as well. So if we design our entity chart here, we put our 9 entities down the side, and then we also have our PK and SK for that composite primary key if we're going to use it. All right, the final step before we start designing our table is to define our access patterns. Let's take a look at those, and we'll break them up into a couple categories. First, there's all the basics around the repository. So there's get and create a repo. There's get, create, list issues for a repo, get, create, list pull requests for a repo, fork a repo, and get all the forks for a repo. Second batch, is all the different interactions you can have with things. So you can add a comment to an issue. You can add a comment to a pull request. You can add a reaction to an issue, a pull request, a comment. A user can star a repository, and then you can get all the stargazers for a repository. Next, there's all the user management access patterns. So create a user, create an organization, add a user to an organization, get all the users for an organization, and get all the organizations for a user. And finally, there's the interaction between accounts and repositories. So you have get repositories for a user and get repositories for an organization. All right, time to dive in and start designing our table, designing that primary key and those indexes to handle our access patterns. First thing you always got to think about is, do I want a simple or composite primary key? And you're almost always going to choose a composite primary key, especially if you have a complex access pattern. That's what we have here, a number of fetch many type access patterns, complex relationships. So we're going to go with that composite primary key. Next thing you want to look at is whether you have any interesting requirements in your data. And I think we have 4 here. The first one is we have a couple different shared resources, and this is pretty interesting. I talked about this with issue and PR numbers, how, when you create an issue, it's going to increment that number up. And same thing with PRs, but they're actually sharing those numbers across each other. So you'd have issue number 1, issue number 2. Then if you create a PR, that's PR number 3. Create another issue, that's issue number 4. So you're sharing that across those. There's also a competition for uniqueness across account names. So not only must the username be unique within all of GitHub, and must the organization name be unique in all of GitHub, but also across those usernames and organization names have to be unique. So you can't have a username of Alex Debris and an organization name of Alex Debris. Those would be conflicting. You only get one sort of account name within GitHub. Another thing that's pretty interesting is that a fork is itself a repo. So a fork has a one-to-many relationship, a repo can have a one-to-many relationship with other repos by virtue of this fork relationship. Because if I fork your repo, what I have is a repo and it needs to show up in all my repo lists, but it also needs to show up in yours as one of the forks of your repo. So that's pretty interesting. Another thing we have is a couple different areas where we're maintaining reference counts. So not only issues and PRs, we're not maintaining how many of those have been created in a repository, but you saw the stars and the forks numbers where, that repository was starred almost 6,000 times, forked over 1,000 times. We need to maintain those reference counts as we're creating those, so we're not querying those on the fly. Last thing is we have this concept of a reaction, and a reaction can be attached to multiple different types of resources. So you can react to an issue, to a PR, or to a comment, which is pretty interesting. And then also there are 8 different types of reactions. So we really need to keep track of a lot of different things going on there. All right, so let's dive in. Let's get started and start modeling out some entities. I'm going to start with the repo entity. You always want to choose sort of a core entity, and this one's pretty core here. You can see it's the parent of 3 different one-to-many relationships. So it's the parent of issues, pull requests, and forks. It's also the subject of 2 one-to-many relationships, as users can own multiple repos and organizations can own multiple repos. Let's start with thinking about those relationships where the repo is the parent entity, issues, pull requests, and forks. And we talked in one of the earlier chapters about how you can actually model out 2 one-to-many relationships in one item collection if you put that parent entity right in the middle, and in one you're scanning forward, one you're scanning backward. The only way that's going to work is if you have one access pattern that goes in a descending fashion and one that goes in an ascending fashion. So let's look at our 3 relationships here. If we look at issues, remember we want to get the most recent issue, and that's by the issue number. So that's going to be a descending access pattern. We're going to get the highest issue and work our way down. Same thing with pull requests there. Pull requests are going to have numbers, and we're going to get that in a descending pattern as well. Finally, with forks, this is kind of interesting. A fork is itself a repo, so we're not going to be able to model a fork in that fork relationship in that main primary key because for someone else that's actually going to be a repo, and then for some people that's going to be looked at as a fork. So it doesn't look like we'll be able to handle 2 one-to-many relationships in one item collection here. So let's get started and let's just model out repos and issues in the same item collection, and this is the pattern we're going to start with here. For that repo, the PK and the SK are going to have the same pattern. It's going to be repo, hash, and then the owner name, and then hash, and then repo name. Because remember that combination of owner name and repo name need to be unique across all of GitHub. And then likewise with issue, we're going to want to put issues in the same item collection as repos so that we can grab the repo and all of its issues. The PK there will be the same: repo, hash, owner name, hash, repo name. And then that SK will be issue, hash, issue number. We can look at that here. We've got a couple items in here. We've got 2 repository items and then 3 issues. You can see that the issues are in the same item collection as their repository there. One thing I want to point out, if you look at this, we're including the issue number in the sort key because that's how we want to sort by it. But if you look at it, these are sorted in an odd way where it has issue 1, then issue 12, then issue 2. What's going on here? That seems out of order. And it deals with how DynamoDB sorts numbers in strings, because even though these are numbers we're sorting by 1, 2, 3, 4, it's actually a DynamoDB string because we have that prefix of issue hash on there first. So when DynamoDB is evaluating strings, it's going to evaluate 1 character at a time. So if you look at it here going left to right, it's going to look, all of them are going to be issue hash, and then it's going to start looking at that number. And then if you're looking at 12 as compared to 2, the first digit in 12 is 1, while the first digit in 2 is 2. So that's why 12 is showing up before 2. So that's not what we want. So we're going to do something else, and I call this zero padding these numbers, where if you're going to have a number in a string, make sure you make the numbers all the same length. And I do that by just zero padding it. So I've zero padded it here to 7 digits. So if I have a number that is only 1 or 2 digits, I'm going to add a bunch of zeros to the front of it so that they're all going to be evaluated equally against each other. So now if I look at that there, as I'm evaluating there, now it's ordered correctly. So I have 1, 2, 3, and then 12 comes last because, again, now it's all an equal length that it's sorting on. So this is a common strategy to use. We talked about this in the sorting strategies chapter. Big thing you got to look out for here is make sure you don't overflow that length that you have there. So make sure you're choosing enough digits so it's unlikely you'll go over it. Here I'm choosing 7 digits. It's unlikely we'll ever get to 10 million issues in a single repository. So I think we should be good there. So just updating that PK and SK for that issue. That SK is actually going to be issue hash and then the 0 padded issue number, not just the blank issue number, but we're going to actually 0 pad it a little bit. And now when I look at it, it looks like this. And now you can see my issues are ordered as I want them. And then I can do that descending access pattern where I fetch the repo and fetch the most recent issues according to the issue number. Let's take a look at the code because I want to show a few things here. First, I just want to show out the structure, which I've done in other examples here, but I just want to walk through it. What I typically do is I have 3 different folders: data, entities, and handlers. That entities folder is going to represent my actual application objects as well as how to serialize them into DynamoDB items. So if I look at that, let's maybe pull up the issues item here. I've got a class of issue. It's got a constructor of all the different things it needs to put in there to identify an issue. It's got this key method that returns the primary key for that item. And then it also knows how to serialize it into an item. So it's got this toItem method where it's going to put all those attributes in there. It's going to make sure to include DynamoDB types and things like that on it. One other thing here, I just want to pull up, we have this, we talked about 0 padding that issue number. So I've just got a method that does that, and I use that in a few places, and it's calling out to a different function called 0 pad number and passing in that issue number. If you look at the utilities here, that's where I've got that 0 pad number function where I'm just passing that in and doing that 000 and then just returning the last 7 digits there. So that's what the entities look like. Additionally, we have handlers. So let's see what maybe let's do the create repo handler. These are just Lambda functions that are handling HTTP requests and then interacting with our data layer. So I have a JSON schema that defines the input schema that I want. So I want an owner name, I want a repo name, optionally a description as well for my repository. Once I do that, I'm just going to create a repo object. That's going to be from my entities directory that we already saw, and I'm going to call out to this create repo method, which is in the data access portion. So let's take a look at that. So if I go into data, I have this create repo, and what I'm doing, I'm just calling put item from DynamoDB, and I'm using that repo item and calling that toItem method that knows how to serialize it into a DynamoDB item. I'm also including this condition expression to make sure that there's not a repo with that existing primary key already, because we can't have conflicts like that. So asserting that and then just returning it to the user. So I like having that 3-part thing where I have the entities, those are my application objects, and also how to serialize them in Dynamo. Then I have my handlers, then I have my data access layer. Let's actually test out some of these requests using Postman here. So here I'm going to create a repo. I've got my base URL configured based on my deployed Lambda serverless service. I also am going to the /repos endpoint. I'm doing a post request, and I'm including all the information that we want for our repository. So the owner name, the repo name, the description, all that. Let's send that up and see if that works. So here we go. We got a 200 OK. It got all this information back for us about the repo. Some of those things are things we haven't talked about, but we'll get to those later on. Let's go ahead and add an issue to that repo as well. Same thing, got that base URL. The path here is going to be repos, and then it's going to be the repo owner name, the repo name, and then the /issues endpoint. I'm making a post request there and passing in this body here, telling me, in this issue to finish the book and get it done. So here we go. Let's send that one up. And again, now we've got that. It's got an issue number 1. It's got a status. It's got all the different things on it. Now we can go and fetch the repository and all the issues, which will again query that item collection and return those to us, most recent issues first. So let's try that. And here we go. We got that repo object here, which includes all that metadata about the repo. And then we have an issues, which is an array and contains all the different issues there. So that's how that works. So that handles the basics around repos and issues. Let's do pull requests while we're here, because pull requests and issues have a lot of overlap. So what we're going to do here, we can't model pull requests in that same main item collection as issues as we discussed because they both have that descending access pattern. So this is what we'll do instead. We'll do that in a secondary index. So on our repo item, we'll add GSI1 PK and GSI1 SK. These are going to be the exact same values we use for our PK and our SK on that repo item. And then we'll also add this pull request item, which is going to have a PK of PR, hash owner name, hash repo name, hash, and then a 0 padded pull request number. Similar concept there to that 0 padded issue number that we did before. That pattern is going to be the same for the SK. And then that GSI1 PK is going to be repo hash owner name hash repo name. So it's going to put it in the same item collection as that repo. And then that GSI1 SK will be PR hash 0 padded PR number. Let's look at our table with a few of those in there. Again, we've got our 2 repo items and our 3 issue items that we had before, but now we've also added these PR items here at the bottom. And one thing I've done is, I could have put maybe all the PRs for a repo in the same item collection, the same main one on that table. But really, if you're not going to do that access pattern of fetch many pull requests right there, I'd split them up into different partitions just so you get a little more even balancing there. And since we're going to handle that in that secondary index, you don't need to worry about this in your primary key. Second thing to note here is that we've added these GSI1 PK and GSI1 SK values to both the repo items and to the pull request items. If we go then and take a look at our secondary index, our data is going to be reshaped, and now what we have is our repo item, our pull request items are in the same item collection. We can do that exact same access pattern we just saw with the get issue or get repo and get the issues for a repo. We can do that same thing now with get repo and get the pull request for a repo. All right, just to close out the basics on repos and issues and pull requests, here's our entity chart. We have the PK and SK defined. Not going to run through that. The big important thing to note there is in that main table, that primary key, the repo and the issue are going to be in that same item collection. If we go in and take a look at our GSI1, we've got the GSI1 PK and GSI1 SK values. Again, big important thing there is that the repo and the pull request will be in the same item collection, so you can get that fetch repo and the pull request for that repo. All right, so we've done the basics for issues and pull requests, but there are some advanced topics, advanced patterns we need to cover here as well. 2 that I can think of. Number 1, auto-incrementing IDs, and then number 2, filtering on open and closed status for both issues and pull requests. So let's get started with that auto-incrementing ID. And if you go look at the items we have in here, remember we have those different issues, those different pull requests. You can see there's this attribute issue number for our issues and pull request number for our pull requests. Let's think about how that actually works. What happens is every time in a repository when you create an issue or a PR, it's giving this auto-incrementing ID. So that first issue you create in a repo is going to be issue 1, the second one will be issue 2, etc. The interesting part is that incrementing number is shared across issues and PRs. So if you've created those first 2 issues in your repository and then you create a pull request, that pull request is going to be number 3. You create another pull request, that's number 4. You go back, create another issue, that's number 5. So they're incrementing on top of each other, which is kind of interesting. So the way we're going to handle this is going to be a 2-step process. Number 1, we're going to keep track of the current issue and pull request count number on that repository item. And when this new create issue or create pull request comes in, we're going to increment that first. So we're going to run an update operation on that repo item to increment that counter. We're going to get that value back, and then we're going to create a new issue or PR using that returned number. Let's take a look at that in code. Here we have the add issue to repo data access function. Add issue to repo here, it's going to pass in an issue. The first thing it's going to do is increment that repo count, and notice that it's awaiting this, so it's actually blocking. It has to do these sequentially. If we go down to that increment repo count, what it's doing is just instantiating this repo object and then calling this update item on that repository item, making sure that repo exists first, and then if it does, it's going to increase that counter by 1. And the counter we're going to be hitting up there is that issue and pull request count. We have this attribute that's keeping track of the total count of issues and pull requests and just incrementing that every time. Further, note that we have these return values all new. This is stating what we want to return from that update item operation, because by default, when you run this update item, it doesn't return anything about the item you just updated. So what we're doing there is say, hey, return us all the values of the item as it looks after it's been updated. Once we do that, we can constitute this repo from item and pass it back. So now we're up here and we've already incremented that count. We're going to keep going. We're going to take that issue that we got passed in and we're going to set the issue number now, and it's going to be equal to that issue and pull request count that we already incremented. And then we're going to run that put item operation to actually insert that issue into our table. For the item, it's going to use that issue to item method and make sure that it doesn't exist there. And then we have our issue added to the table. So that's how we handle that auto incrementing ID. The second advanced topic we have here is we need to be filtering on open and closed status of issues. So if we go back to when we were learning about this application, this is the issues list, and you'll notice that it has open or closed. So when you're searching for issues or pull requests, you're either looking for open or closed issues. So we need to figure out how to handle that. If you look at our items in our table, there is a status property, but it's an attribute. It's not in our primary key. So we're not able to sort of filter and query on that directly in our primary key, which isn't great. So there are two approaches that we could handle this and that you need to think about with filtering. Number one is you could build it into the primary key somewhere. It wouldn't be in the primary key of our main table, but it could be, in the primary key of a secondary index where maybe we build status into that and we could do a composite primary key like we talked about in that filtering section. The second option here is we could use a filter expression or do client-side filtering. So what we do is fetch more items than we actually need, and then we'll just filter out either open or closed as we want to. We're going to go with that one here. We're going to use a filter expression. And a couple reasons I thought about doing this is number one, there are only a couple different statuses that we're filtering on. It's not like we have to filter on a lot of different things. So since it's either open or closed, I think we should be okay there. It's not we don't have to overfetch too much. And then again, we're also only returning, I think, 25 items per request, which means it shouldn't be that hard to fetch 50 or 75 and then filter down as needed. One thing I do want to say is in the migrations chapter, which is the next chapter, we're actually going to migrate away from this pattern because I actually don't like using it here, and I'll talk more about it, why there, but we will migrate away from this. So let's take a quick look at the code to handle this. This is our data access function, get repo and issues. We're going to be using that query. This is going to be on the main table, and we're matching based on the partition key and the sort key. But one thing we've added here is this filter expression where we're either saying, either the attribute does not exist, where it won't exist on that repository item, because remember we're fetching the repository and the issues, or if that status property does exist, we want it to be equal to this particular status value that we're passing in here. Here's the status value that we're passing in, which is going to be passed in with our function. So this will either be open or closed. It's going to get that. And so then when we query and get that back, we're only going to receive the open item or the open issues or the closed issues as requested. So let's test that out with some actual requests. We'll do that get repo and issues function here. We have our repository. And we have one issue there, and it's status open. So by default, it's not going to include a filter, or it's just going to get us all the open issues. But now let's go update that issue, and we're going to update this issue here, make a post request, and change that status to closed. So let's do that. We've done that here. Now our issue is closed. So let's go back to that get repo and issues. And now we see we're receiving 0 issues back because we're only trying to get the open issues. So let's turn on our parameter here. And now we've added this status equals closed parameter, this query parameter. If we send that up, now we do get this issue back. We get these closed issues. So we have that closed issue back. So we can see how that filter is being applied there with that query parameter. All right, so that's how we handle that filtering on open and closed status. Let's move on to the next entity we want to model, and that's repos and forks. And this is kind of an interesting one. Just a reminder of what you have here. When you look at your repository, you can see everyone that's forked your repository, which basically means they've made a copy of the contents that also points back to your repository. Here's an example here. I have a repository for the dynamodbguide.com that people have forked, and you could see the list there. And the big access pattern we have there is we want to be able to fetch all the people that have forked from a particular repository. Now, there are a few interesting parts about this. Number one, it's a one-to-many relationship because there can be many forks for a single repository, but a fork will point back to one repository. The other interesting thing is a fork is itself a repo. So we need to make sure that that repo can be accessible within the normal repo paths for users for whom it is a repo. So that means we need that get repo access pattern. We need get repo and issues, get repo and pull requests for this forked repo. So this is what we're going to do here. We're going to add a GSI2 and create an item collection that includes a parent repo and all of its forks. If it's a parent repo, then the GSI2 PK will be repo hash owner name hash repo name, which is the same as we've used for the regular partition key there as well. If it's a fork, then what we're going to use for GSI2 PK is repo hash in the original owner name. So, if you fork that DynamoDB repo of mine, this would say repo hash Alex Debris hash dynamodbguide.com. And then that GSI2 SK would be fork hash and then the forking owner. So whether that's a user or an organization that's forking that, they would put their name there. So if we take a look here are a few examples of the DynamoDB book repository. That first one is the actual book, and then the three below it are just different forks of that book. And then you can see the GSI2 PK and SK there. If we take a look at GSI2, we can see that all of our items are together in the same item collection, both that parent repository and all of its forks. So if we look at our entity chart, we had fork listed as an entity on there, but a fork isn't really a separate entity in the main table. So we're actually just going to scratch that out there. If you look at that GSI2 index though, the fork does exist there. So we'll have these patterns here. Again, that repo is just going to have that same pattern it's always had: repo hash owner name hash repo name. If you look down at that fork though, if a repository happens to be a fork, then that GSI2 PK will be repo hash original owner hash owner name, and that GSI2 SK will be fork hash owner name. Next thing we want to model out is repos and stars. And just a reminder of what that is, there's a many-to-many relationship between users and repos via this star relationship. So a user can star a repo, indicating that they like something about that repo. A user can star multiple repos, and a repo can be starred by multiple users. So that's why it's that many-to-many relationship. The interesting thing here is that a user can only star a repository one time, because we don't want to allow a user to sort of jack up star counts for their repository by clicking it a bunch or writing some API bomber to do something like that. So whenever you need to maintain that uniqueness, you're probably going to have an item that's actually tracking that relationship. So this is what we're going to do here. We're going to create this star entity. The PK there is going to be repo hash owner name hash repo name, and then that SK is going to be star hash and that starring username. So if we take a look here, what we have here, we have that repository entity. The interesting thing here is we're now modeling two of those relationships in a single item collection. So if you look at the bottom there, we have repo and stars, to where if you want to get a repo and all the stargazers for that repo, you start at that repo item and scan forward to get all those different users that have started. We still have that repo and issues access pattern here as well. So when you want to get the repo and all the issues in a repo, you start at that repo item and you scan backwards to get all the issue items sorted by most recent. So let's take a look at our updated entity chart. We've now added this new star entity, which we didn't have on our chart before, but now we realize we need something to keep track of that. Again, it's going to have that PK of repo hash owner name hash repo name, which is going to put it in that same item collection as the repo entity and the issue entity. The important part there is the repo is between the issues and the stars, so you can handle both of those relationships there. Now, we have something interesting with both stars and forks, where we want to maintain reference counts for both of those items on a repository. So if you go back to our repository view here, this is the AWS SDK.js. You can see that this repository has been starred nearly 6,000 times, and it's been forked over 1,000 times. And there are some repos that are way higher than that, tens of thousands or hundreds of thousands of stars or thousands of forks. So what you want to do is maintain a count of those on the repository item itself, rather than every time you show this page querying all the stars and all the forks to see how many there are. So we'll handle that here. When you're doing a reference count like that, what you need to do is you need to use a transaction, this transact write item, and you're going to do two things. Number one, you're going to increment this counter on that parent object, which is going to be that repo. And then you're also going to write that item, whatever that related item is, whether it's a star, whether it's a fork, you'll write that item with a condition expression to make sure that it doesn't exist. And then if it does exist, if there's already a star or if this repository has already been starred by that particular user, this is going to reject that part of the transaction, which will roll back the entire transaction and make sure we don't increment that counter as well. Let's take a quick look at the code to handle that. So here in our data access layer, we have this add star to repo function. We're passing in a star. We'll also create a repo once we get in there, and that's when we'll create these transact items, the multiple items that we're going to put in our transaction. First, we're creating that star item and ensuring that it doesn't exist because we want to make sure that this user has not already starred this repository. In addition, we're going to update that repo item. We're going to make sure that repo exists to make sure they're not starring a repo that doesn't exist and making some shenanigans there. The next thing they're going to do is update the star count on that item. So what they're doing is incrementing it. So they're saying set that star count equal to the current value plus that increment here. That increment is 1. So we're just incrementing that value by 1. Now, if either of those fails, either because the repo does not exist or because this user has already starred that repository, it's going to get rolled back and that whole transaction won't have happened. So let's check that out by making some actual requests. So we have this add star to repo request that we're going to do there. It's going to be repos hash the repo owner and the repo name, and then on the /stars path, we're going to make a post request. In there, we're going to post which user is actually doing the starring. If you had a proper authorization system, you do this via the auth token or wherever it's being passed there, but I'm not building that out for this particular thing. Here, Alex Debris, he's pretty vain, so he's going to star his own repository. So let's set that up there. We make that request and we see that star happened. Let's see what happens if he tries to star that again. Oh, user has already starred this repository, so we're not going to allow him to star it multiple times. But if we want to get in there with a different user, a similar copycat, that user can star that repository. Now, the interesting thing is that star count is on that repo item. So let's go back to our get repo and issues request that we saw earlier. We'll send that up. And now we can see on the returned repository that we have there, we have this star count of 2. So it's showing us whenever we return that repo item in any of these different requests, it's been updated with that reference count so that it's easy to see those. All right, so let's move on to our next access pattern. We're going to model out another entity, which is comments. So just a reminder what we have here. This is an example issue, and if you look there pointed in red, people can comment on issues. So they can add additional context, discuss how to handle the particular issue, and that's what it's going to look like there. A couple notes around comments. There's going to be a one-to-many relationship with a parent and the comments. You can have multiple comments on a particular target. There are 2 types of targets. So a comment can be attached to an issue or to a pull request because there's conversation around both of those items. And then the final thing is we want some chronological ordering around those comments because, you can leave multiple comments on these issues or pull requests, but we want to see it like a conversation to where you can see oldest to newest. So here's the pattern we're going to use here. We have issue comments and PR comments. The PK pattern we're going to use for issue comment is going to be issue comment in all caps, then owner name of the repository name, and that issue number. And then that sort key will be issue comment hash and the comment ID. And for that comment ID, we'll use that KSU ID, which we used a number of times, which again, it gives us uniqueness on a particular item. So it's easy to generate a unique ID, but it also has a prefix that includes some timestamp data. So then they are sortable chronologically. So that's great. So that's how we'll handle the issue comments. Same thing with PR comments. Big thing there, we're going to change issue comment to PR comment and then issue number to PR number. So looking at our entity chart, this is what we have here. Got that new issue comment, got that new PR comment into our entity chart. All right, so we have one more entity we need to map out that's related to repositories before we move on to user management related things, and that's the reaction. So just to get a sense of what we're looking at here, down there outlined in red on this particular issue, you can see the thumbs up, and there are 56 people that have thumbs up this particular issue. And so what you can do, these are called reactions, and you can add reactions to things like issues, pull requests, or comments. And just indicate some sort of reaction to it. It can be happy, it can be sad, it can be a rocket, it can be a heart, all kinds of things. So interesting things about reactions. Number one, there's a one-to-many relationship between that target and the reactions because multiple users can react to a particular target. Again, those different target types are issues, pull requests, and comments. And there are 8 different types of reactions that we need to keep track of. So there's a thumbs up, there's a thumbs down, there's a heart, there's a smiley face, there's a crying face, all that. One thing that we need to keep track of is, there's going to be a reaction item per target. So a user can react with a smiley face to an issue, but they can also react with a smiley face to a comment within that issue. So we need to have distinct items going on here that's tracking all this. And a couple things we need to handle there. Number one, uniqueness, because again, we don't want to allow a user to react to the same target multiple times in the same way. They can react in different ways to the same target, or they can react the same way to different targets, but not the same way to the same target. Also, we need to maintain reference counts. So you saw in that example how there were 56 people that had thumbs up that particular comment. We want to make sure we have a count on that parent item of how to handle that. One thing we need to think about with, especially with that reference count and around uniqueness, is do we want to have 8 different attributes on a particular item like the repo to have, a smiley face count, a thumbs up count, a thumbs down count, or do we want to have a map, which is just a reactions attribute that has 8 different properties in it, and it could be thumbs up, thumbs down, heart, different things like that. I'm opting for a map here. You can really go either way. I sort of like the cleanness of containing it all within a map, and I don't have to parse out all those different entities, but you can really go either way here. So let's take a look at our entity pattern for these reactions. And I'm just warning you, it's going to be a bear, but we'll walk through it. So basically a reaction is going to look like this, where the PK is going to be target type and then reaction, all caps. Then it's going to be owner name, repo name, target identifier, and the reacting username. So let's walk through what we have here with an example of a PR comment reaction. So first thing we have there in bold is going to be PR comment reaction in all caps. So that has that target type of PR comment because they're reacting to a comment on a PR. It's not the PR itself. It's not a comment to an issue. It's a comment on a PR. So it's a PR comment reaction. Then we have the owner name of the repository, which is Alex Debris. We have the repo name of the repository, which is DynamoDB book. Then we have the target identifier, which for a PR comment will include both the PR number as well as the comment ID. If your target here is just a PR, then it'd just be the PR number. If it's just an issue, it's just the issue number. But whatever it is to uniquely identify that particular target. Then finally, the last thing we have there is that reacting username. And the reason we need all of this information in there is because we need to make sure it's unique across all of those different dimensions, because we want to allow users this flexibility to react in different ways to different things as much as they can, but while still making sure they're not gaming the system by reacting multiple times to the same thing. So let's take a look at what that looks like in code. And first we'll look at our issue entity just to see what it looks like to store sort of that reference count of all these different reactions on there. So here is my issue class. One of the things I can put in my constructor is this reactions property, which is by default just going to be an empty map. And what we're going to do is we're just going to store the value of that on my issue item. So when I call this to item, I'm going to have this reactions attribute, which is going to be a map, and it's going to call this format reactions method here, which gets down here. And what it does is it just iterates over that reactions. It actually iterates over all the possible reaction types and creates a counter in that reactions map for the number of people that have reacted in that way to that particular target. Same thing when we're parsing it from an item back into an object in our application, we'll be able to parse that and figure out how many people have already liked that sort of thing. Let's go look at the function to actually add a reaction to an issue. This is what we have here. So this is that add reaction to issue function. Again, we're going to use that transact write pattern that we used to maintain reference counts in the previous section about stars and forks, same type of thing. So we'll have 2 transactions here. The first one is going to update this issue reaction item. So this is the one that's maintaining evidence of this particular user's reaction to this particular target. And one thing we're doing here is making sure that this reaction is not contained in this reactions property. So what we have is we have a set attribute on this issue reaction, which just maintains all the types of reaction they've already reacted to this one. As part of that updated expression, we're going to add that reaction to the set. But also first we're making sure that it doesn't already exist, which would indicate they've already reacted to it. The second thing we're doing is updating that reference count. So on that issue item here, we're making sure that that target exists, that issue exists already. And then we're incrementing this counter. And you can see what we're doing here is we're actually accessing a nested attribute in a map. So we're saying in this reactions map, access the reaction name attribute and then increment that by 1, and where the name will be the actual reaction that's passed in. So whether that's a +1, a -1, smiley, disappointed, anything like that, that's going to get incremented here so that we can keep track of all those different reactions on that particular target. So let's go test that out with Postman. So we have this add reaction to issue method. It's a post request. It's going on that target, so that issue 1 that we've already created in DynamoDB book, the reactions path there. What we're doing in our body is just saying which reaction we want to do. We're doing the smile. I'm also including the username again because I don't have authorizations set up in this particular one. So if I send that up, it's going to say, okay, I received it. Now let's try and send it again, which it should reject. Yep, user already added smile to this issue, but we can change and maybe we do a -1. Okay, we got that. Try that again. User already added that. If we try a new user that wanted to do -1, we can do that. So we got that in there. So we've added 2 -1s. We've added a smile. Let's go back to that get repo and issues, which we've done before. We'll fire that up. It's going to return that repo item as usual. It's also going to return that issues item. If you look down here, we've got all these reactions stored in a map here, and you can see that we've got 2 -1s stored there, and we've also got 1 smile stored there. So you can see how we're updating that reference count, so we don't need to go get all those every time. It's very efficient that way. All right, so that closes out reactions and really everything related to that core repo entity and all the stuff that branches off of that. We can update our entity chart with that PK and SK. I'm not going to run through that again because it's so long. Let's move on to the last area of our application. This is around user management. And with user management, we have 2 main entities, and that's users and organizations. And the interesting requirement there is the account names are shared across users and organizations. So it needs to be unique across all users and all organizations. That means if I created my user Alex Debris, I couldn't create an organization named Alex Debris either. It needs to be unique across all those. Given that, we're going to need to build that uniqueness into the key, and we're going to need to make sure it works across both of those keys. So here's the pattern we're going to use here. For both users and organizations, or for users at least, the PK is going to be account hash username. Same with the SK, account hash username. Organization is going to be the same one, but with org name. So PK is account hash org name, SK is account hash org name. So again, you get uniqueness across these accounts because that name is going to be included in there and making sure you don't step on each other's toes. Here are a couple examples here. So I've got 2 actual user accounts in there, Alex Debris and Danny Developer. We also have 1 organization account in there, that's Megacorp. You can notice here I've got that type attribute on there of users and organizations. So that's how you can tell the difference between them, but you can't actually tell the difference just based on the primary key. You can't tell if it's a user or an organization. So now that we handled that uniqueness across those account names, let's look at the next part, which is this is a many-to-many relationship because a user can belong to multiple organizations, but also an organization has multiple members in it. And many-to-many relationships can be tough with NoSQL, with DynamoDB, because you're trying to understand how to get a fresh view of that data from both sides of that relationship. One thing we can do here, we can think about each side, and particularly with the users to organizations, you can see it's a pretty shallow relationship there. So if I'm browsing around and I look at my organizations, all it really says is the organizations I'm a part of and their names. It doesn't have a lot of detail about the organization itself. I'd have to click into that and drill into it to get that. So what we're going to do, we're going to use that shallow duplication technique that I talk about in the many-to-many chapter, where on this user item, we're going to have this organizations attribute. That's going to be a map, and it's just going to say each key in that organization will be in that organization's attribute will be the name of an organization, and then the value there will be the role that they have in there. So whether they're a member or an admin or an owner or anything like that. Now, the nice thing about using this shallow duplication pattern is it basically chops off half of that many-to-many relationship that we don't need to worry about, and it turns the other side of it into a one-to-many relationship that we know how to handle. We've done a lot of times before. So now what we'll do is we'll just add a membership item there. So we've got our user, we've got our organization. Additionally, we're adding this membership item that the PK is going to be account hash organization name, and then the SK is going to be membership hash username. So every time a user is added to an organization, we'll create this membership item to record that. We can look at that here, and now we have our users, we have our organizations, we have our membership, and now it's easy to query both sides of those relationships, because if we want to get the user and the memberships for that user, we look up that user and look up that organization's attribute there. On the other side, if we want to find an organization and all the members for that organization, we can run a query on that organization's item collection, and it'll include both that organization and all the members in that organization. So let's update our entity chart here. We've got 3 new entities: user, organization, and membership, with the PK and SK values that we talked about. So let's move on to the next part of user management, and this is around payment plans, right? Because if I'm GitHub, I want users, I want organizations to pay, sign up for my higher level tiers so I can make some money. One thing that's interesting here is that there's a one-to-one relationship with users or organizations and a payment plan. So a user or an organization can't have multiple payment plans. It's just going to be one. Almost always when you're modeling a one-to-one relationship in DynamoDB, you're just going to have that on that item itself, and that's just going to make it easier to look it up and store that The two exceptions there would be if you wanted to get that related entity, you know, the payment plan, if you want to have different access patterns. So find, if you want to search by payment plan and find some different things, you might split it out separately that way. A second thing you might do is if that related entity had a lot of attributes, a lot of data attached to it, and you didn't want to fetch it every time and pay that read cost for getting that related entity, you might split it out into a different item that way. But neither one of those are really the case here. So we're just going to attach it directly to those user or organization entities. And so that's what we've done here. If you look at those users and organizations that we had before, we've just added this payment plan attribute that it's a map, so it's a complex type. It can hold a lot of data, such as the type of plan, the plan start date, things like that. But we're not going to model that out as a separate entity there. All right, so this is the last set of access patterns, and we're really just merging our two worlds here. We've spent a bunch of time working with repos and all the related items. We spent a little bit of time on user management, working with accounts, and now we need to merge those. And there's a one-to-many relationship between accounts and repos, because a user can have multiple repos, a organization can have multiple repos, but an individual repo is only going to belong to one account, either that user or organization. And when we're fetching those, we want to fetch by the most recently updated. That's how GitHub handles this. So if you sign in and you're looking within your organization or your individual user, you'll see repositories by the most recently updated. So we need some ordering that way. So here's what we're going to do. We're going to add a new global secondary index. This is going to be GSI 3. We can't use GSI 1 or GSI 2 because they're already being used by the repo entity. And here are the patterns we're going to have. For both the user and the organization, the PK and SK will both be account, hash, and then account name. So whether that, for a user, that's going to be a username. For an organization, that'll be the organization name. Likewise, for that repo, the GSI3 PK will be that account hash and the repo owner, which will be that account name. And then that SK is going to be hash and then updated at. And this is what that'll look like when we get all those together. First of all, let's look at our different accounts and repositories we have here. If I look outlined in red, there's the GSI3 PK and GSI3 SK values that I've decorated on my repo and account entities. If I reorganize that into that GSI3 PK, it looks like this. And you can see that in an individual item collection, I have my account and I have that account item, whether that's a user or an organization. And I also have the different repos in my account. Notice that those repos are all at the beginning of my item collection, which is going to allow me to run that query, scan index forward false. I'll start at that account item and work my way backwards. That's going to give me the most recently updated repositories. So if I update my entity chart here, now I have this GSI3. I've got GSI3 PK and SK values for the repo, for the user, for the organization to make sure they're all in the same item collection, and I can get that get account and get repositories for account access pattern. All right, so that concludes the GitHub example. I had a lot of fun with this one, trying to work through something that I use every day and think about how I would model it in DynamoDB. It was a nice complex application with a lot of different access patterns, so we had fun there. Let's review what we built. Our table will have a composite primary key using generic names like PK and SK for those primary key values. We also had 3 secondary indexes, GSI1, GSI2, and GSI3, and all those had those generic composite primary keys as well. Just looking at our entity charts here, we have a bunch of different entities here: repos, issues, pull requests, stars, issue comment, PR comment, reactions, users, membership, organization. We didn't have a payment plan because that's going to be attached directly to a user and an organization, but we have that on here since it was in our entity chart. We can also look here at that GSI1. We've got repos and pull requests because that's how we get that get repo and pull request access patterns. For that GSI2, we have repos and forks, which again, forks are just repos, just a different view of that repo, but that allows us to do that get repo and get forks for repo access pattern. And then finally, last GSI3 we have here, has repos, users, and organizations, because that allows us to say, hey, give me that account and give me all the organization or the repositories for that account as well. Now, as I was working through the book, I had a lot of people ask me about how do I migrate my DynamoDB tables, or how do I evolve as my application evolves, and I heard you there. So what we're going to do in the next chapter is we're actually going to take this data model and we're going to evolve it. We're going to have a couple new access patterns, we're going to have a couple changed access patterns, and show, migrations in DynamoDB aren't that scary. So check out that next chapter.